The security requirement for a block cipher is that the block cipher, when I pick a key, if I pick a random secret key, that this behaves basically like a random permutation. And what I mean by that is that no attacker can tell the difference between whether they're working with a block cipher or whether they're working with a random permutation. At least no attacker that runs in polynomial time. No efficient attacker. No attacker that runs in a reasonable amount of running time that's feasible, that could finish within our lifetime. So to formalize that, I want to talk about how we would formalize that definition. And we're going to do that with a game. Remember, we defined security for in CPA using a game. So now we're going to have a game that defines what it means for a block cipher to be secure. And here's how this game is going to work. There's going to be a referee, and there's going to be an attacker. And what the referee is going to do is the referee is going to construct two boxes, two black boxes. One box, the referee is going to fill in by picking a secret key randomly for the block cipher, and then hard-coding that secret key inside there and having the innards of that box be something that computes encryption under the block cipher with that particular secret key. Okay, so this is a black box that accepts an input and encrypts it under that secret key and returns the result. And the other black box, the referee is going to fill in with a random permutation. So you could conceptually imagine that the referee fills in this truth table entirely and hard codes the truth table into that black box. Now that truth table might be ginormous, so you might not actually want to do that. So if you prefer a more feasible version of that, you can imagine the way this black box is going to work is it's going to have a truth table that's initially not filled in. And when you give it an input, it's going to look that up in the truth table. And if it's already there, it's going to return the answer found in the truth table. But if it's not, it's going to randomly fill in that entry in the truth table, but making sure that there are no repeats anywhere on the right-hand side of the truth table. Okay? So these are two boxes. The referee is going to take these two boxes. They're going to paint the outside black so you can't tell just from looking at it which of the kind of box you've got. The only way that you have of potentially distinguishing them is sending some inputs and looking what the outputs you get. The referee is going to take those two boxes and stick them behind his back and shuffle them around randomly and give you the two boxes. He's going to give the attacker the two boxes, but without indicating which is which. Okay, so here's the attacker. The attacker has got two boxes, and the attacker can interact with those boxes in any way the attacker wants. The attacker can send any inputs to either box and observe what output comes back from that box. And could do this over and over again. The only limit on the attacker is the attacker is limited to run in a feasible amount of time, like in polynomial time, or using at most 2 to the 60 steps of computation, or, taking at most 10 years of computation power to do this. And then the attacker's objective is to try to guess which box is which. Okay? If the attacker guesses right, they win. If they guess wrong, they lose. With me so far? What probability do you think you're sure you could achieve? What probability of winning this game are you sure you could achieve as an attacker? Yeah? 1/2. How'd you get a half? Just guess randomly and you'll be right half the time. Okay? So now the security requirement for a block cipher to be secure says that the attacker can't do any better than that. Well, not much better than that. At most, a half plus some negligible function. And what do I mean by negligible? Well, same as last lecture. It could be something like 1 over 2 to the 60 or smaller. Some incredibly small number, like 1 in a billion, billion, billion. Okay, so what this is saying is if the attacker's probability of winning this game is even slightly more than a half, even just a little bit more than a half, like is 0.6 instead of 0.5, or is even 0.51 instead of 0.5, then we say the block cipher is not secure. But if they can't do any better than half plus a teeny, 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 teeny little bit, basically they can't get any better than a half, then they say then we say the block cipher is secure. Okay? So it's secure if for all attackers, if this is true for all attackers, no matter what attack algorithm is used, that run efficient for all efficient attackers. Like for all attackers that run in polynomial time, or for all attackers that use at most 2 to the 60 steps of computation, or that will finish in at most 10 years while using at most 1,000 supercomputers, something like that. Okay? So that is the security definition now for a block cipher. And what this encodes is attacker has no hope of distinguishing the block cipher from a random permutation. It's as good as if you had a random permutation.